Good afternoon and welcome to my presentation. First of all, let me thank all of you for coming to this virtual seminar, and also thank the organizers for creating this opportunity for us to present our research and seek potential collaborations. In this presentation, I'm going to talk about my research on silicon-based Terahertz-Integrated Sensors and Systems, which many believe will be the next generation of radio frequency chips that we will use for a plethora of growing and emerging terahertz wave applications. A little about my lab and myself in this slide. Of course, I have to acknowledge the considerably less hairy version of myself in this pre-pandemic photo. But after that, I received my Ph.D. in electrical and computer engineering from Rice University in 2018. And I also did my postdoc at UCLA in 2018 for a period of around 9 months. And then I joined UCF in 2019 as an assistant professor. My lab's name is Terahertz-Integrated Circuits Lab. I currently advise 3 PhD students. I also have 2 undergraduate researchers supported by Summer REU. Our group focuses on the analysis, design, and development of high-frequency integrated circuits and on-chip antennas for the purpose of unlocking the terahertz spectrum with energy-efficient and high-performance systems in communications, sensing, imaging, and computation applications. A little about the status of my teaching. I have taught and will continue to teach 3 undergraduate courses in fundamentals of microelectronics and signals and systems. I've also developed a new graduate course called Terahertz-Integrated Systems, which is currently in the course catalog. This course is about teaching novel circuit techniques, new system design paradigms, and applications in the millimeter wave and terahertz frequency regimes, which are between 30 gigahertz and 1.5 terahertz. To introduce my research, I'd like to first give you a quick overview of what we actually refer to as terahertz waves, or what is the terahertz spectrum. Taking a look at this figure, we see the electromagnetic spectrum that extends from radio frequencies and microwaves all the way to what we know as optical light. But there's a region in between, which is commonly referred to as terahertz gap. And the reason behind that is both electronics communities and optics and photonics communities are facing limitations in trying to generate and detect signals in this part of the spectrum. So it's more of an underutilized part of the spectrum. We're going to discuss these limitations in the next slides. But first, let's take a look at the applications of terahertz waves. Terahertz waves can be used in high-speed wireless links, which is, of course, the central topic of next generation 6G systems. They can be used for security imaging and explosive detection, for high-resolution medical imaging and pharmaceutical applications, as well as broadband spectroscopy and material detection. And the reason behind that is because terahertz spectrum material molecules have vibrational and rotational absorption modes in this spectrum, which are unique and can be used to detect material. There are also some emerging applications, such as hyperspectral 3D imaging radar, which can be deployed in mid-range and can have resolutions comparable to human vision for autonomous driving or UAVs. And there are also emerging applications in near-field 3D microscopy and nanoscopy. And microdoppler radar that I'm going to present a demonstration of this application to you for remote vibration detection, and also terahertz computation. In order to see what motivates my research, we need to take a look at current terahertz technologies and their limitations. One category of current terahertz technologies are narrowband continuous wave systems. In electronics, we have oscillator-based systems, which generate a single tone radiation with narrowband modulation. We also have quantum cascade lasers, which are able to generate high power, higher terahertz frequencies, but they are cryogenic systems. And there are also other optoelectronic techniques such as terahertz beat note photomixing. The other category are broadband terahertz time domain spectroscopy systems that are used in spectral imaging systems. These systems currently are based on femtosecond lasers and photoconductive antennas. For example, taking a look at this figure here, we see that a femtosecond laser and photoconductive antenna system is integrated inside this bulky and expensive unit. And these systems usually have low energy conversion efficiency and limited repetition rate and reconfigurability. To overcome the limitations of the current status of the technology, we propose to build fully integrated broadband terahertz systems as the next generation of terahertz technologies. These systems will have a high DC to terahertz efficiency, conversion efficiency, and scalability. They will have broadband array beamforming capabilities with rapid digital reconfigurability and modulation. So basically our goal is to turn this bulky optoelectronic unit into a fully integrated chip that it may lead to the proliferation of terahertz systems. The first project that I'm going to present is about silicon-based terahertz pulse radiators with the objective of creating pulse sources that can generate a broadband spectrum with precision synchronization between digital clocks and radiated pulses, and also with pulse shaping and amplitude modulation capabilities. These systems are based on a very simple fundamental principle that if you have an inductive antenna, and if you store a DC current in these antennas, then you can use a transistor switch to suddenly disconnect this current, and then this stored energy will be released into radiation. So we developed an architecture based on this principle to turn digital edges into radiated terahertz pulses. Here on the right figure, you can see some of the chips that we developed based on these ideas, we were capable of achieving a record 1.9 picosecond pulse width radiation in silicon with repetition rates up to 10 gigahertz, which is much higher than the 100 megahertz repetition rate of femtosecond lasers, with a peak effective isotropic radiated power of 80 milliwatts. And then we use these chips for broadband spectroscopy, high-speed long path wireless links, and microdoppler radar that I will show you in the following slides. We also made arrays of these pulse radiators for coherent spatial combining of terahertz pulses radiated from single chip arrays. So the goal here was to scale up the radiation power while keeping the broad spectrum. In order to build these chips, we introduced a time-based beamforming architecture, which is different than what is used in traditional phased arrays. In traditional phased arrays, for the operation of the array, the delay is introduced in the radio frequency path, but we developed a time-based architecture that introduces delay in the digital path. We made arrays, single chip arrays out of this architecture. Here you can see an 8-element chip in 90 nanometer SiGe by CMOS, and we were able to combine these pulses with a pulse width of 5.4 picosecond and scale up the EIRP to 1 watt. And each of these elements has a delay generator with 300 femtosecond resolution, and we use them to demonstrate hyperspectral imaging and gas sensing. I also would like to introduce you to one of my recent projects that I'm currently working on and might have potentials for collaboration. This project is called Hybrid Electronic Photonic Coherent Terahertz Wave Generation and Sampling. So here our goal is we want to use the best of both worlds and synchronize femtosecond lasers with digital electronics to be able to use, to build a hybrid measurement and characterization system. We made a proof of concept setup that includes an optical detector and an electronic radiator, and we're capable of making spectroscopic measurements. And now I'm going to show you some of the applications that we demonstrated with these chips. The first application is hyperspectral imaging. We made a transmission-based imaging setup and used our chips to radiate terahertz pulses to turn on a broad spectrum, and then we could, at each frequency tone in a range from 30 gigahertz to 1.1 terahertz, we were capable of making hyperspectral images. For example, in this figure in the bottom, we see the terahertz image of a rock sample with a 4 millimeter thickness. And these are images taken at different frequencies, or you may want to call it different colors. And we see that as the frequency goes up, we are able to see more information with detailed resolution from within these rock samples, which can be used for many applications. We also perform terahertz gas sensing using these chips because gas molecules have rotational absorption lines in the terahertz spectrum. And we use these chips along with a cylindrical gas cell with a controlled pressure. We introduce different gases versus a background gas, and we're capable of demonstrating this application by measuring 572 gigahertz absorption line for ammonia or 753 gigahertz absorption line of water. We also use these terahertz chips for microdoppler radar. Well, Doppler effect is a very well-known effect, and in fact, in practice, it's every day used by, for example, police cars to find out the speed of vehicles. But one of the unique features of terahertz radiation is that when we generate these very high frequency signals with an extremely high frequency stability, then we are capable of detecting smallest vibrations and disturbances when these waves are reflected off a vibrating surface. So we demonstrated this application, and here I'd like to show you some of the results. So I'm going to play the original sound that we used to vibrate a reflecting surface, and then the extracted sound that we basically demodulated this microdoppler effect from a terahertz wave to extract this vibration from a remote distance. So this is the original sound. And this is what we could basically extract from these terahertz waves. So this is one of the enabling applications of terahertz waves, that it's not possible to use lower frequencies. With lower frequencies, they're going to experience smaller Doppler shifts that is not going to be detectable. We also use these chips for long path wireless channel characterization for high-speed wireless links, and we're capable of showing wireless channel characterization up to distances of 110 meters. And I believe there's a lot of potential for near-term collaborations on different technologies that we can build with these terahertz chips. Currently, I'm focusing on my NSF career proposal to build a universal terahertz system that has rapid reconfigurability of arbitrary waveforms, which could be one of the potential applications is terahertz computation. My near-term collaborative, the near-term collaborative opportunities that I think of are we can build terahertz gas sensors for precision remote gas detection. We can also build long-range remote sensing radars for material detection, vibration sensing, and also we can, that was in far field, and in near field, we can perform sub-wavelength microscopy for the detection of micro to nanoscale features and defects in materials. And in long term, one of the major applications is going to be the emerging 6G communication and sensing applications that we need to build terahertz wireless transceivers and high resolution 3D imaging radar for autonomous vehicles and UAVs. And also silicon-based terahertz computation is one of the paths that I'm following, and I'm seeking collaborations, which using these terahertz chips, by generating an arbitrary waveform, we can basically encode data in this spectrum and unlock this spectrum for high throughput computing in a low cost and energy efficient platform. And finally, I would like to thank all of my students and members of my lab, and also my current and former collaborators at UCF, UCLA, and Rice. I would be happy to address your questions.
So Mahdi,